Welcome to Physics Hub. Today is 14th of April 2019 Sunday, and here I am with a new set video. So as you know that we upload a set video on every Sunday, and it usually consists of 10 solved problems from different topics of physics. We generally upload the question paper on our Facebook page little earlier so that you can try to solve the questions and match your answers when the solutions are uploaded. Now one thing, whenever we upload a video, we distribute it into different relatable playlists. So go through the playlist and you will be able to get videos as per your choice. And keep a track of our community post as well. It will help you to make your base of physics strong. Now without any further delay, let's start today's set video. So this set contains 10 questions from complex analysis. The first question reads like this: what is the value of the integral 0 to 2 plus I mod z bar square dz along the line y equals to x by 2? And you are given 4 options. So this is the straight line y equals to x by 2 and I equals to this integral, and we have to find it along this y equals to x by 2. Now along the line OA, x equals to twice y. Now we know that z equals to x plus iy. So we are trying to write everything in terms of y. So we placed in place of x 2y, then plus iy, therefore 2 plus I into y. Therefore dz equals to 2 plus I into dy. Now the limits of z is given 0 and 2 plus I. We are converting the limit into the limit of y. So when z equals to 0, y equals to 0, the calculation is shown here, and when z equals to 2 plus I, y equals to 1. Therefore the integration is transformed into this 0 to 1, 2 minus I, z bar equals to 2 minus I into y, so 2 minus I whole square into y square, and dz equals to 2 plus I into dy. Okay, now carrying out this integration, we are getting the value of I equals to 10 by 3 minus 5 by 3 into I, and it is matching with option 1. So option 1 is the correct option. Moving on to question number 2. Find the value of the integral closed integral c sine pi z square plus cos pi z square by z minus 1 into z minus 2 dz, where c is the circle mod z equals to 3. Now what we will have to do? First, check the configuration or the given contour. Mod z equals to 3. How does it look like? It looks like 3. It looks like this. So mod z means the origin of the circle is situated at the origin. Okay, at this point 0 0 1 2 3. Now we have to find the poles. So here z equals to 1 and z equals to 2 are the two simple poles which are lying inside the contour 1 and 2, this and this. Now what we are doing, we are just writing I by separating these two terms. So a into z minus 2 plus b into z minus 1 equals to 1. We are keeping this term on the numerator aside. So 1 into this term, so we are equating it with 1. So this one you have done your plus 2 level. So first we are putting z equals to 1 and we are getting the value of a equals to minus 1, and by putting z equals to 2 we are getting the value of b to be equals to 1. Okay, so we are just writing I equals to closed integral c, and we are writing fz, this whole term, as fz. So fz by z minus 2 minus, by putting the value of a, fz by z minus 1, where fz equals to this sine pi z square plus cos pi z square. Now we have to find out the residue at z equals to 2 and z equals to 1. To find out the residues, we have used the simple formula fz, z minus 2 by z minus 2 equal to f of 2. And similarly, residue at z equals to 1 equals to f of 1. Now using Cauchy formula, we get the integration I equals to twice pi I into sum of residue, it's f of 2 and the minus sign then f of 1, because we have taken twice pi I common. So we are getting the value of the integration I equals to 4 pi I, and it is matching with option 3. So option 3 is the correct option. Moving on to question number 3. Choose the correct value of the integration over dz by z square sine hyperbolic z from the following. Now, first of all, we have to draw the contour. Okay, I'm sorry, the contour has not been given in the question, but the contour is z minus 1 equals to 2. So z minus 1 means the origin is lying at z equals to 1, and the radius of this circle is 2. Okay, although the circle is looking like egg, but it's a circle. I'm sorry for that. And it has radius 2. The figure is actually wrong. Yes, it is correct, because this is 2 unit and this is 2 unit. The origin of this circle is lying at z equals to minus 1, and it has radius of 2 unit, because 2 is here on the right hand side. Now we have to find out this integral. Now here we see that z equals to 0 is a pole of order 2, and sine hyperbolic z equals to 0 equals to sine n pi, means sine iz equals to sine n pi, because sine iz equals to I sine hyperbolic z, and this I is conjugated in this 0, so we get iz equals to n pi. Therefore z equals to n pi I. So minus sign will appear here, so minus or plus doesn't matter here. Now z equals to n pi I are the poles for this integrand. Now, but none of them is lying inside this contour. So what we have to do, we cannot apply Cauchy equation here, because we have two types of poles, z equals to 0, and for sine hyperbolic z we are getting these poles. So to find out the residue, we have to apply another thing, not residue theorem. We have to apply this expansion method. So what we are doing, we are just writing sine hyperbolic z at e to the power z minus e to the power z by 2, and we are just expanding it in finite series. We see that only the even order terms are surviving and the odd order terms are vanishing, and we are taking z common. So even order terms is cut, and when we are taking z common, so only even order terms are surviving here. So 1 plus z square by 3 factorial plus z to the 4 by 5 factorial. So when we are taking it to the numerator, a minus sign is appearing. So this term to the power minus 1, we have just expanded a plus b to the power minus 1, and we are getting this, and we got the coefficient of 1 by z as minus 1 by 6, and we know that the coefficient of 1 by z in the expansion of this integrand gives you the residue. So residue at z equals to 0 equals to minus 1 by 6. Therefore the integration I equals to twice pi I into minus 1 by 6, that is equals to pi minus pi I by 3, and it is matching with option 1. So option 1 is the correct option. Moving on, question number 4. Using complex variable techniques, evaluate the real integral 0 to 2 pi sine square theta by 5 minus 4 cos theta d theta. Now whenever you see this type of problems, 0 to, in the limit 0 to 2 pi means a circle is forming, then theta related terms, then what you will do, you just take z equals to e to the power I theta. So a unit circle z equals to e to the power I theta. Now we are just trying to write cos theta and sin theta terms in terms of z. So writing cos theta by this, and d theta equals to dz by iz, and we are replacing these values of cos theta, d theta in terms of z, and we are getting this I equals to 0 to 2 pi sin square theta by 5 minus 4 cos theta d theta equals to half 2 sin square theta means 1 minus cos 2 theta by 5 minus 4 cos theta d theta, and we have to find out this sin square theta by this. So this integration I equals to real part of half of 0 to 2 pi 1 minus cos 2 theta minus 1 minus I sin theta. Why we are writing this? Because we want to write these terms in terms of exponential with z terms. Okay, so cos 2 theta plus I sin 2 theta can be written as e to the power twice I theta, and e to the power twice I theta means z square. Now we are just replacing the theta values by z value by its corresponding z values. So e to the power twice I theta becomes z square, and cos theta becomes this half into z plus 1 by z, and d theta dz by iz. Now we are getting this form. Now we are very familiar with this form. We know how to find out this integration. So first we determine the poles. So poles are determined from by putting the denominator equals to 0. So 2z square minus 5z plus 2 equals to 0, and from here we get the two values of z as half and 2. Now we are considering unit circle, so z equals to half will lie inside the circle and z equals to 2 will lie outside the circle. So we have to consider only z equals to half to evaluate the integral. Now residue at the simple pole z equals to half is this. We have used the standard formula and we got residue at z equals to half as 1 by 4. Therefore the integration is real part of 1 by 2i into integration of this. So 1 by 2i integration is 2 pi I into sum of the residue. Using Cauchy equation we are getting pi by 4, because there is no imaginary term, so it is real term. So real part of this pi by 4 is pi by 4, and is it matching with option 3? So option 3 is the correct option. Question number 5. What is the value of the integral 0 to infinity dx by x to the power 4 plus 16? Now to solve this problem, let's consider this integration. Integration over c dz by z to the power 4 plus 16, where c is a closed contour, this whole contour consisting of the upper half tau of a large circle mod z equals to r, and the real axis from minus r to plus r. Poles of 1 by z to the power 4 plus 16 are given by z to the power 4 plus 16 equals to 0, means z to the power 4 equals to minus 16, and it can be written as minus 1 can be written as e to the power twice n plus 1 into pi I. And from here we can determine the poles. Z equals to 2 into e to the power twice n plus 1 by 4 into pi I, and this exponential function can be written in terms of cos and sine. Now by replacing the value of n 0, 1, 2, 3, we get the successive poles. So z power of z is 4, so we will get 4 poles. So putting n equals to 0, we are getting the first pole z1. Putting n equals to 1, we are getting the second pole z equals to 2. And by putting n equals to 2, we are getting the third pole z3. N equals to 3, we are getting the pole z4. Now this is your contour. Now we see only z1 and z2. These two poles are lying, z1 and z2. These two poles are lying inside the contour. So these two poles, only these two poles will be utilized to find out the integral. The other two poles will have no role in determining the integration. Okay. Now to determine the integration, we have to find the residue at these two poles z1 and z2. So firstly, residue at z equals to at z1 means 2 e to the power I pi by 4. So what we are doing, fx by f prime x. So we are just replacing. We are trying to find out the residue, and this is a standard residue formula, and we are getting 1 by 32 into 1 minus 1 by root 2 minus I by root 2. Similarly, we are finding the residue at z equals to twice e to the power I 3 pi by 4, and we are getting 1 by 32 1 by root 2 minus I by root 2. Therefore the integration value twice pi I into sum of residue at poles within C. So we are getting pi by 8 root 2. Now this is the total contour, which contour C, which comprises of this contour, this semicircular arc, plus this line. So we are just writing them as the separate integral minus r to r fx dx plus this semicircular arc tau, this is tau, and this is the real axis. So minus r to r, then tau, equals to pi by 8 root 2. Now we have to find out this term. So firstly, in mod of integration over tau dz by z to the 4, this is less or equals to mod dz by z to the 4 minus 16. And z, if you take z equals to r e to the power I theta, means dz equals to r I e to the power I theta d theta, means mod dz equals to r d theta, and mod z to the 4 equals to r to the 4. So r by r to the power 4 minus 16, and d theta means pi. Now when this r goes to infinity, this term goes to 0. Means when if you put r equals to infinity, then this term will vanish. So minus infinity to plus infinity, when r tends to infinity, 1 by x to the power 4 plus 16 dx equals to pi by 8 root 2. Therefore, look, this is an even function. So 2 into this 0 to infinity equals to dx by x to the power 4 plus 16. Now pi by 8 root 2 was there, so this 2 coming this side, so pi by 16 root 2, and it is matching with option 2. Option 2 is the correct option. Moving on to question number 6. The value of the integral 0 to infinity sine mx by x is, when this is note, when the integrand has a simple pole on real axis, it is deleted from the region by indenting the contour. A small semicircle, this small semicircle having pole is drawn, this lower one. Consider the integration over c e to the power imz by z dz, where c is a large semicircle, mod z equals to r, indented at z equals to 0 pole. Let r be the radius of indentation. There is no singularity within the given contour. Hence, by Cauchy theorem, integration over c e to the power imz by z dz equals to 0. So it can be written by decomposing it minus r to r. Then this small arc CR, take care of the sign on which direction you are traversing the contour. Then small r to capital R, then this big semicircular arc CR, and the sum of them will be equals to 0. Now substituting minus x for x in the first integral and combining it with the third integral, we get small r to capital R e to the power imx minus e to the power minus imx by x dx plus this integral plus this integral. This equals to 0. And it can be written as twice I into small r to capital R sin mx by x dx plus this integral as usual equals to 0. Now this capital big integral CR e to the power imz by z dz equals to, by putting z equals to r e to the power I theta, we get this, and taking mod, we see when r tends to 0, this whole integral goes to 0. Okay. Now for the small integral, we see CR equals to, so we are trying to write it in terms of theta. So z equals to r, small r e to the power I theta, because the radius is here small r, and the limit of theta is pi to 0, because we are going from this to this, so the angle is pi and we are going towards 0, theta equals to 0. So pi to 0. So pi to 0 e to the power imr e to the power I theta by r e to the power I theta, and dz equals to I r e to the power I theta d theta equals to pi to 0 I e to the power imr e to the power I theta d theta. Now when r goes to 0, means this term vanishes 1. So y d theta means I minus pi I. So when r tends to 0, this term is producing minus pi I. So this term vanishes and this term equal to minus pi I. So twice I into 0 to infinity, we have put r tends to 0 and r capital R tends to infinity. So twice I 0 to infinity sine mx by x dx minus pi I equals to 0. Therefore sine mx by x dx equals to pi by 2, and it is matching with option 3. Option 3 is the correct option. Now question number 7, what is the integral? Value of the integral minus infinity to plus infinity 1 by t square minus r square cos pi t by 2r dt. So in complex plane, f of z means this integrand equals to 1 by z square by minus r square, real part of e to the power I pi z by 2r. So we are just trying to write this term in terms of the complex function z. Now the pole of this function is z minus r into z plus r equals to 0. In this way we can find the poles. So the poles are situated at z equals to plus r and minus r. Now you have to find out the residue. Residue at z equals to r is this I by 2r, and residue at z equals to minus r is this. So this is the standard formula we have used here. Therefore I equals to twice pi I into sum of residue I by 2r plus I by 2r means minus twice pi by r, and it is matching with option 1. So option 1 is the correct option. Moving to question number 8, find out the value of the integral 0 to infinity ln x square by x square plus 1 dx. Let C be the closed curve where tau 1 and tau 2 are semicircles of radii epsilon and r respectively, and center at the origin. So this is the integration. We have to find out the value. Since the integrand has a simple pole z equals to I inside C, and z equals to minus I is not lying inside the contour, so we don't have to consider that. And since the residue at the pole is so residue at z equals to I is minus pi square by 8i. Now we just you may ask, why should I write ln I to be equals to I pi by 2? So here I have shown ln I means I equals to root over minus 1. So ln minus 1 to the power half, and half is coming here, and minus I can be written as e to the power I pi, so I pi by 2. Therefore value of this integration equals to twice pi I into minus pi square by 8i, so minus pi cube by 4. Here I have used Cauchy equation. Now this closed integral can be decomposed in this way: minus small r to minus epsilon, then this, then epsilon to r, then this big integrand. Okay, so we are getting 4 terms. Let z equals to minus u in the first integral. So this thing we have already done in the previous or some previous problems. So we are putting z equal to minus x there. So here we are putting z equal to minus 1. So it's dummy variable, so it doesn't matter. So whether we put z equals to minus u or z equal to minus x. So z equals to minus u in the first integral on the right, so that ln z equals to ln minus u equals to ln u plus ln of minus 1. So ln u plus pi I. So dz equals to minus du. Also let z equals to u, so that dz equals to du, ln z equals to ln u in the third integral, this integral on the right. Then using 1 we have this. Where is 1? 1 is this, and this, and this is equals to minus pi cube by 4. Now let epsilon tends to 0 and r tends to infinity. In this problem, whenever we take a small circle indentation, then this semicircular radius will be very negligibly small. So epsilon is very tends to 0, and this r should be infinitely large. So r tends to infinity. And when we take epsilon tends to 0 and r tends to infinity, we see that the integral around tau 1 and tau 2 approaches 0. Therefore the remaining two terms, 0 to infinity and 0 to infinity, this equal to minus pi cube by 4. And when we separate it out, we see that we are getting 3 terms, and that is equal to minus pi cube by 4 and after simplification, and this term we can find out, this is standard integration tan inverse u, and we are taking it to the right hand side, and we see this term equals to pi cube by 8. Now what we are doing, we are equating the real and imaginary parts, and we find that 0 to infinity ln u square by pi u square plus 1 du equals to pi cube by 8, and this imaginary term produces 0. And we need to find out this term. So this term is equals to pi cube by 8, and it is matching with option 2. Option 2 is the correct option. Moving on to question number 9. If 0 less than p less than 1, then the value of the integral 0 to infinity x to the power p minus 1 by 1 plus x dx is. Consider closed integral c z to the power p minus 1 by 1 plus z dz. Since z equals to 0 is a branch point, choose c as the contour of this figure, where the positive real axis is the branch line, this, and where AB and GH are actually coincident with the x-axis, but as shown separated for visual purpose. The integral has a simple pole z equals to minus 1 inside this c, and residue at z equals to minus 1 is e to the power I pi p to the power minus 1. Therefore, the integration value goes twice pi sum of residue. Now we have to find out this. We have to find out in terms of x. So what we are doing, we are using the same method. We are just decomposing the whole integration into several parts. So from a to b, then b, d, e, f, g, then g, h, then h, j, r, h, j, a. Okay. So we have written like this, where we have used z equal to x e to the power twice pi I for the integral along gh, x e to the power twice pi I. Since the argument of z is increased by 2 pi in going around the circle b, d, e, f, g, so 0 to 2 pi. So argument has increased by 2 pi I, so that's why we take z equals to x e to the power 2 pi I. Taking the limit epsilon tends to 0 and r tends to infinity, and noting that the second and fourth integrals approaches 0. Second and fourth, these two integrals approaches 0, and in the in few previous problems I have shown how it is 0. We find that this plus this, only two terms are surviving here. This is equals to twice pi I e to the power p minus 1 into pi I. Therefore, we are taking common 1 minus e to the power twice pi I into p minus 1, and we are taking common this term 0 to infinity x to the power p minus 1 by 1 plus x dx, and after simplification we get the value of this function, or value of this integration 0 to infinity x to the power p minus 1 by 1 plus x dx equals to pi by sine p pi, and it is matching with option 3. Option 3 is the correct option. Now the last question of this set, let u of x equal to e to the power ax cos by be the real part of a function f of z equals to u of xy plus ivxy of the complex variable z equals to x plus iy, where a, b are the real constants and a is not equals to 0. The function fz is complex, analytic everywhere in the complex plane, if and only if. So this is the function you are given, u e to the power ax cos by, and we are writing ux means differentiation of u with respect to x. So according to Cauchy-Riemann equation, this formula should be held, ux equal to by. So taking derivative with respect to x, so a e to the power ax cos by equals to del v del y. Therefore b equals to a e to the power x cos by dy equals to a by b e to the power x and by. So we are taking with integration with respect to y, so the integration constant will be function of x. So this is equation 1. In the same way, comparing 1 and 3, where is 3? Because something is missing here. Yes, 1 and 3, something is missing here, so fx equals to fy. Okay, so I'm telling you again what you will do. Uy equals to minus vx, another Cauchy-Riemann equation is there, and from there also you will get some equation and integration constant fy, and comparing 1 and 3, some I have forgotten to capture that part, but you are smart enough to do that by yourself, so do it and comment down. So you will get fx equals to fy equals to 0, and you will get b by a equals to a by b. Therefore, a is equal to b square, equal to b equal to plus minus a. You just try to solve this problem. If you cannot solve this problem, let me know in the comment section. I will upload it again, and you will get b equals to plus minus a. So I have tried my best to provide the solutions in great detail. Irrespective of this, if you have any doubts, confusion or queries, you can comment down below. I will try my best to clarify them all, and any kind of suggestions are always welcome. So this is all for today, guys. If you find this video helpful, please give it a thumbs up, and if you are a new visitor of this channel, please subscribe the channel and press the bell icon so that you never miss any update. Keep sharing, keep loving, and keep exploring the wonders of physics. And finally, thanks for watching.